Welcome everyone, and thank you for tuning in for another Up Close with Solarplaza. Today, I'm very happy and honored to be joined by Parikhit Sinha, a senior scientist of sustainability research at First Solar. At the end of last year, Ricky co-published an article at the academic journal Joule called The Value of Stability in Photovoltaics. And today, we will unpack this together. But before we jump into this topic, Ricky, I'd like to give you the floor to introduce yourself and maybe give a bit of a background on where the inspiration for this topic came from.
Thanks, Lorena. Yes, I'm Parikhit Sinha with First Solar. I'm a senior scientist in sustainability research. I work in the area of product stewardship, which includes product safety, life cycle assessment, and end-of-life management. So one of the fun aspects of my job is I occasionally get to work with academic researchers on interesting sustainability topics. And so in the past year or two, I've collaborated with Ian Marius Peters at the German Research Institute Jülich on this value of stability study. It was inspired by early work from the US Department of Energy that was part of their Sunshot program. And in that program, they were trying to accelerate the deployment of photovoltaics by setting very aggressive targets for levelized cost of energy, or LCOE. And in their work, they hypothesized that stability or degradation is equally important to efficiency in achieving those aggressive targets. We figured out that there's a way to quantitatively evaluate their hypothesis using a similar study that my colleague Marius Peters wrote a few years ago, which was called The Value of Efficiency in Photovoltaics. In that study, he actually quantified the change in module cost that would go with improvements in module efficiency when you're going after a certain target LCOE. And we figured we can use that same approach to look at stability.
Great. I think it's an important conversation to have in an industry that is so focused on generating green energy for the world. So we ourselves need to become a sustainable industry. But I'd like to first clarify the title of this piece is The Value of Stability. What do you mean about stability? What are you referring to?
Yeah, we have two kind of main terms to talk about with stability. One is the degradation rate. So this is the long-term degradation that occurs with solar panels with their change in nameplate power over many years. For example, currently degradation rates are about 0.5 to 0.6% per year in most solar panels. And then there's the product lifetime as well. So oftentimes it's assumed that a solar panel is a 25 or 30-year lifetime product, which is based on the typical warranties that are available for solar panels. So when we talk about stability, we're talking about improvements in either the degradation rate or the lifetime.
Mm-hmm. And you mentioned something interesting about the life cycle and how this is generally around 25 years. And a very interesting line I got from your piece was that this is to some extent a choice or an assumption. Could you expand on this? And if this is an assumption, what would then extending the lifetime perhaps mean for solar professionals?
Yeah, I often get this question when I'm working on projects and communities ask, what is the lifetime of a solar panel? And we usually give that same convenient answer. Look at the warranty, it's 25 to 30 years. But actually, there's no reason why a panel can't be longer lived than that if it's still providing value to its owner. And so in our paper, we tried to define it using an economic lifetime rather than just a warranty lifetime. And what this means is the economic lifetime is the duration over which the solar panel is providing greater value to its owner than the owner would receive by replacing that solar panel. And so it's really a function of how quickly that panel degrades and what is the cost of replacement. Overall, we found that for solar panels with 0.5% per year degradation rate, the ideal lifetime is actually 35 years rather than just the 25 to 30. And then if you hit the sunshot target, which is a 0.2% per year degradation rate, the ideal lifetime goes up all the way to 50 years, which is almost double the common assumption today. So it really gives a lot of room for improvement. And one other point is that we were trying to convey a shift in mindset in this paper, away from just thinking about the upfront cost of a solar module or a solar system, but thinking more long-term, including the value of maintaining that system over a long period of time, because there's no requirement that a project is decommissioned after 25 or 30 years. It could be operated even indefinitely if you were to maintain it properly and replace components as they fail. And the longer you operate that system, the more valuable stability becomes. Because if you choose to go with a technology that's less stable, you will be losing out on a lot of energy production over those long period of time. And so it really changes the mindset away from just initial cost to overall lifetime energy production.
That'd be quite the paradigm shift if we're looking at a project from 25-year lifetime to 50-year lifetime. And I think it speaks to perhaps a broader shift in our society of being very much about replacing or starting afresh rather than maintaining. But I also think that in order to really speak about these findings, then you probably need to put an economic valuation to it, as you've mentioned with the models, or at least put a number, really, what is the economic value of stability? I think that is what our professionals would want to know.
Right. That is kind of the core of the paper, is to quantify the value of doing these improvements. And so again, the way that it was done is to find the change in module costs that balances the improvement in module degradation rate while hitting that target LCOE. And what we found is that for every 0.1% per year reduction in degradation rate, you would generate value of about 1 to 4 cents per watt in the module cost. And that seems like a small number a few years ago, but today that's a pretty large fraction of the overall selling price of a solar panel. So if you're talking about 4 cents per watt, that's about 15% of the cost of a solar panel. So that small change in degradation rate can really make a big improvement in value. Another way to think about it is with regards to efficiency. That 0.1% per year reduction in degradation rate corresponds to a 0.3 to 0.5% absolute percentage improvement in module efficiency. So that original hypothesis from Department of Energy that stability is equally important to efficiency is found to be true.
Quite interest reduction costs that you're pointing out, Ricky. But what if I were to switch the question around, flip it over? We just spoke about the economic cost of stability. What is the sustainability cost of stability?
On the sustainability side, I think it's common sense to understand that if you have a longer lived product, you're going to generate less waste over a period of time. Specifically, if we look at the next 30 years through 2050, the amount of end-of-life waste that will be generated will be 60% less with a 50-year product than a 30-year product. And we can also look at year-by-year cases. So we can model using what's called a Weibull curve, which is a curve that looks at the probability of loss in a given year. How much waste will be generated over the next 30 years? And again, if you have a 30-year product, the peak amount of waste will be 8% in a given year. And if you have a 50-year product, it'll go down to 5%. And so that's a 40% reduction in the peak amount of waste in a given year. And why that's important is that we are currently planning our recycling infrastructure for that future peak. And so we can actually downsize the requirements for the recycling infrastructure if we have longer lived products. And that's something that we're actively working on. First Solar has been providing recycling services for the last 15 years. And we see that in the next post-2030 timeframe, end-of-life volumes will start to increase. And so we're looking at scaling up our recycling infrastructure, and these improvements in stability will play a role in that plan.
Yeah, great. Sounds like you can save costs on your plant life cycle management and the cost of the modules, but even in the post life cycle, if you're looking at the costs of a recycling facility or how much product that recycling facility will be receiving, you can reduce those costs just by having a longer life cycle plant.
That's right. And there's one more aspect of sustainability that is very important, which is the environmental footprint of solar, whether we're talking about carbon footprint or water footprint or energy payback time, energy return on investment. These parameters are quite dependent on lifetime energy production. And so if we're able to have longer lived products, we have greater lifetime energy production, and that proportionally reduces the environmental footprint of solar. And in terms of energy return on investment, you can have values even exceeding 100, which are very high values that make solar very sustainable in comparison to other energy options.
Well, that would be a great thought to have a fully sustainable project life cycle and beyond it. But then to close off, Ricky, I have a few final questions, maybe perhaps an overarching view of what are the main challenges and the main progress that you see in stability and sustainability.
Yeah, so over the years, there's been quite a lot of statistics maintained on degradation rate, and specifically, researchers have looked at improvements over time, like pre-2000, post-2000 manufacturing, and there have been reductions in overall degradation rates that are currently down in the 0.5 to 0.6% per year range. And at First Solar, we've also been working pretty hard the last few years on lowering that degradation rate through both understanding how the solar cell degrades and the module packaging around the solar cell, which includes the encapsulation, the edge seals. And we've been able to reduce our warranty degradation rate from 0.5% per year down to 0.3% per year. And we're also looking at ways to get down to that sunshot target of 0.2% per year. And overall, I think the challenges that the industry faces are related to the pace of innovation. So when you look at how both solar cells and panels are changing, there's a lot of variation now in the size and the thickness of solar cells, in their metallization, also in their encapsulation and in terms of backsheets and encapsulants. And so all these changes have to be vetted with accelerated life testing, with outdoor testing, to determine their impact on stability. And if the pace of technological change exceeds the pace of testing for reliability, then you can end up with some surprises. And so that's what we have to guard against. And all these innovations are very important for continuing the progress that we've seen, but the stability, without, if we inadvertently impact stability, then in the long term we'll see some consequences.
Oh, that's a great closing remark. It sounds like this needs to be an industry-wide conversation, because indeed the speed of innovation cannot come at the cost of sustainability or stability, as you mentioned, especially if given this article, the cost of stability and sustainability can actually be a positive one, right? It doesn't have to be a negative one at all. But thank you so much, Ricky, for the comments you have made today. And I'll make sure that we have linked your article as well as any other content pieces if anyone's interested in continuing reading on this topic and keeping an eye on what First Solar is doing in terms of sustainability and solar modules. Thanks again, and I hope that people enjoyed listening in.